Hi guys, hope you've had a really lovely Easter holiday, eaten loads of chocolate, had a good rest, and basically just kept yourself safe. So before the Easter holidays, you were looking at drawing graphs, getting something that looks a little bit like this, plotting the equation, shading the region that you want to discard, making sure you label your line, and being left with a white section, which is called your feasible region, normally labelled R or F. And what I'm hoping you realise that within that region you get all sorts of feasible solutions. They all give a solution that satisfies the inequalities. However, only one of them is optimum. Now, these were all less than or equal to or greater than or equal to inequalities, which is why they're solid lines. And that means that points on the line could be solutions. I've never seen one which is dotted. However, I wouldn't put it past the examiners to do something like that. So just be on the lookout. If it's dotted, you obviously can't have a solution on that line. Now, to find the optimum point, there's two different methods, ruler method and vertex testing method. I'm going to show you both today. I haven't really got a preference. The examiners normally tell you which one to use, to be honest. Ruler method tends to be a bit quicker. I find vertex testing just quite easy, to be honest, if a little tedious. So let's look at vertex testing first. It's pretty much what it says on the tin. We're just going to test the vertices. So this is my region, and you'll see that it's got 5 vertices around it. I'm maximising, so I wouldn't bother looking at 0, 0. That's not going to maximise profit or cost, whatever this may be. So I'm ignoring 0, 0. Doesn't mean you always do. A is quite clear to read off from the graph. It is the point 0, 5. Point D is quite clear. That's 5, 0. And I think you'll agree B is 4, 3. C's not as obvious, and we have to really be careful here. We can't just assume. It's definitely 5, and that looks like 1.5. But like I said, we can't just assume it's 1.5. I'm going to write it down because I know it's 1.5. However, if I was doing this in the exam, I'd check it. And the way we check it is, look at the inequalities that have made that point. So what's made that intercept there? So the two equations are x equals 5 and 3x plus 2y equals 18. So if I substitute 5 in here, 15 plus 2y equals 18, so that means that 2y must be 3. So yes, it is actually correct. Y is 1.5. Lovely. They often throw one like that into the exam, so you have to use simultaneous equations. You can do it on your calculator. Now I've got those 4 vertices, I want to know which of them gives the maximum profit. So I've got my objective function over here. I'm going to substitute each vertex into 5x plus 7y and choose the biggest. So, point A, 5 times 0 plus 7 times y, I get 35. 5 times 4, 7 times 3, So I get 20 plus 21, 41. 5 times 5 plus 7 times 1.5, 25 plus 10.5, 35.5. And then the last one, I'm doing 5 times 5, and then 0 plus 7. So I've just got 25 there. So I'm maximising. I want the biggest one. So my answer is vertex B. I want to make 4 of whatever x is, 3 of whatever y is, and I'm going to assume this is profit. So I need to make 4 of these, 3 of these, and I get a £41 profit. So the hardest part of vertex testing is determining these vertices if you've got to do them all using simultaneous equations. It gets really tedious. If we look at the ruler method, I'm using the same graph, so I wouldn't necessarily have all these on here labelled, but it's a good start anyway. The exam will often do that for you. If I look at my objective function, at the moment we don't know what v is, because v is any number. We're trying to maximise it. But if I put x and y equal to any number and then plotted it on my graph, I should get a load of parallel lines because the gradient will be the same. And the only thing that will change is the intercept. So that is exactly what I'm going to do. I'm going to choose a number that these two go into quite nicely. So 35 makes sense. You can choose any number, but you want to try and make your life as easy as possible. So 5 and 7 clearly go into 35, just makes the points a bit easier to plot. I'm going to look at the 2 points 0 blank and blank 0, because that's how plotting a line is the easiest, I thought personally. If x is 0, y would be 5. If y is 0, x would be 7. And I'm going to plot these now. 7, 0, and 0, 5. Now, please forgive my straight line here. I spent ages trying to figure out how to draw a line on here that is straight, and I can't do it. So, that's one line. That's my objective function when it's equal to 35. And I am going to roughly label that. If you chose a different number, you'd have a different line, but they would all be parallel to each other. So you might have one down here, you might have one up here. However, you want to try and avoid having a tiny little line down here that wouldn't be very accurate, or a line up here. Because the idea is you would lie your ruler against this line, and your ruler would then move backwards and forwards parallel to my line, parallel to your own line. So I'd lay a ruler against this green line here, and I'd move it parallel. And this is actually the only use I've ever found for a set square. Having the set square and the ruler up against it, I can slide it up and down and it will stay perfectly parallel. It's quite easy here to see that if I move this parallel, the last point that I'm going to hit with my ruler will be point B here. So when you are maximising, it's the last vertex you want. If you're minimising, it's the first one. So when you choose a value here, try and use a sensible one. You want your line to be within the region somewhere. You don't want it to be up here, because then you've got to move the ruler a little bit further, and then it might start slipping and not be very accurate. So I found that B is my solution. B is the 0.43. So actually, I don't need to test every vertex now. All I have to do is find out when X is 4 and Y is 3, what is the value of V, and we've already done it, it's 41. So the benefit of this over the vertex testing is you only have to test one vertex. The disadvantage, I guess, is you've got to draw this correctly, and if you don't choose a value that works nicely, you can have a very misleading line. What I'm going to look at now is what happens if you get a solution that isn't an integer. So most examples of this kind, you want whole numbers, so it might be how many items to make, how many people, that kind of thing. And it's quite unusual that you want a decimal answer. What happens if you do get a decimal? How do we turn that into an integer solution? Well, this is a problem I was looking at, and I've got a solution already. X is 1.75 and Y is 4.25. Now, I'm minimising here. That's not hugely important right now. And actually the constraints are not too important right now. They will be really important in a second. So, I want you to imagine in your region you have got this solution here. But we want a whole number. So let's imagine this is the number of Easter eggs made. X is one type of Easter egg, Y is something else. We need to make whole numbers. So we want to choose a value, an integer solution, which is close to these two. We can't just round up, because if I round that up to 2 and I round that up to 5, that might still be in the shaded region. What if I called that 2 and rounded that to 4? I don't know whether that falls within the feasible region. So what we have to do is test the points around it. So I could call that 1 or 2. I could call that 4 or 5. And it gives me 4 different sets of coordinates. So 1 and 4, 1 and 5, 2 and 4, and 2 and 5. Those are all the 4 points which surround this vertex. I need to check which of them actually fall within the feasible region. And the way I do this is by considering the inequalities that formed that region in the first place. So this first column here is my first inequality, the second one is my second, and the third column here is my third inequality. I'm going to check to see if these work for each of my points. So let's look at inequality 1. 1, 4. 1 plus 4, no, it's not greater than or equal to 6. So I'm going to put a cross there, and there's no point even considering the other inequalities for 1, 4. It does not lie within the region. It's actually fell outside for that one inequality. Let's check 1, 5. If I put 1 and 5 in here, yes, 1 and 5 work. So does 2 and 4, so does 2 and 5. So they're all okay. Let's go to the second inequality. Again, I'm not going to look at this one because it's failed. If I put 1, 5 in, 1 plus 25, no, that doesn't work. So I'm going to put a cross there. If I put 2 and 4 in, that gives me 22, so that one actually works. If I put in 2 and 5, 2 plus 25. No, that one's too big, so that one fails as well. Now I can't just assume it's this one. I've got to check that this one actually works for this inequality as well. So 3 times 2, take away my 4. Well, yes, that one is certainly less than or equal to 15. So my point, my integer point, is 2 and 4. And then I could work out the cost for that as well. So it would be using this, 2 times 2 plus 4. So the cost would be, let's say it's £1, £8. Okay, so the idea is get your solution. You would find this using simultaneous equations most likely. Round up, round down, and you get 4 points to check. Check that they work for each of your inequalities. And if you had a choice of 2, I know I've only got 1 here, but if you did have a choice of 2, you'd work out the cost for both and you choose which one is the smallest. What I'd like you to try from there, please, is page 158. I'm going to ask you to do questions 1, 2, 3 and 4, because you can actually do them on the diagram in the book. Just use pencil and then you can rub it out. You're using a mixture of vertex testing and the ruler method, the objective line method. Check the answers in the back. If there's any problems, contact me and let me know. Thank you and best of luck. Bye for now.